Hello, my name is Jonáš Kulhánek and I would like to present you the work that we have done together with my colleagues Eric Derner and Professor Robert Babuška. We focus on deep reinforcement learning applied to visual navigation. In the work I will be presenting, we have transferred our prior approach from simulated environments to a real-world setting. So in visual navigation, we have an agent that moves in a 3D environment. It could be a robot, for example. It has a set of discrete actions, like, for example, move forward or rotate left or others. And the only sensor that the robot has is an RGB camera. The agent is given an image of a target and it tries to use its actions to locate the target and to get as close to it as possible. So before the advent of deep reinforcement learning methods, people usually used simultaneous localization and mapping methods, where we first reconstruct the map of the environment and then we apply a planning algorithm to find the shortest path to the goal. In the case of deep reinforcement learning, we do not need an explicit map of the environment. The agent is represented as an end-to-end neural network, where the input is the camera image and the output is a probability distribution over a set of actions. If it reconstructs a map of the environment, it does it implicitly either in the neural network parameters or in its state. Unfortunately, current deep reinforcement learning approaches work mostly in simulated scenarios. In simulated scenarios, you can generate as much training data as you need, and these methods usually require millions of images. Training these methods in the real world is prohibitively costly. Also, these methods often rely on different kinds of signals. In various approaches, segmentation masks are used as another input to the agent. Also, the distance to the goal is used as a reward for the agent during training. Perhaps the biggest problem with current approaches is that they rely on the simulator to stop the agent after it reaches the target. Unfortunately, in the real world, there is no simulator that would stop the navigation after the agent reaches the goal, and the agent would continue exploring the environment. Even random policy would at the end reach the goal with the probability of 1. Therefore, we force the agent to detect if the goal was found by using a spatial stop action. After the agent applies this action, the navigation is stopped, and the agent receives the reward of 1 if it reached the target or 0 otherwise. So since we cannot train the agent in the real world, we need a simulator. For this reason, we have built our own simulator, which is based on DeepMindLab 3D environment simulator. The simulator uses Office-like environment. On the right, you can actually see 4 images that were generated from our simulator. For a simulator, it is important that it is fast, so that we are able to generate images from the environment quickly enough, so that the training does not wait for the simulator to render images. Also, it is important that we are able to perform some kind of domain randomization, so we effectively increase the number of training samples that we have, but more importantly, the trained policy generalizes better to new environments. In our case, we change the placement of objects in the environment, and we also change lighting conditions. Now let me talk about the architecture of our system. So in the picture, you can see an overview of the architecture. As the input to the agent, we use the observation and the target image. They are both passed through several convolutional layers before the resulting features are concatenated and passed through a few more convolutional layers. This is denoted as conv_base in the picture. And so the resulting features represent both the camera observation and the target image. Now the environment is partially observable. Therefore, the agent needs the whole history to be able to generate the next action. For that reason, we use an LSTM module. It is a recurrent neural network that updates its internal state and gradually incorporates new observations into it. We also use the last taken action and last reward as another input to LSTM. The output of LSTM is used as the input to both the actor and the critic. The actor represents the policy distribution over action, and the critic is used in the actor-critic algorithm to reduce the variance of the policy gradient updates. To improve the training performance, we use auxiliary tasks. All the modules on the right part of the diagram are parts of the total loss function. We just sum all the individual losses. And the first two auxiliary tasks, the pixel control and the reward predictions, are taken from the Unreal method published by Jaderberg in the year 2016. The pixel control task trains another policy that outputs the color of each pixel if a specific action was taken, and the reward prediction outputs the next reward. We also add 3 more auxiliary tasks specifically designed for visual navigation. The first one predicts the depth map of the input image, while the other two output the camera image and the input target image. In a sense, these tasks work in a similar fashion as autoencoders. The narrow part of the network is, however, shared also with the actor and the critic. The idea is that the output of convolutional base would represent the input and target images, and this would help with training, since reinforcement learning is quite noisy and it is difficult to learn useful features only from the reward signal. Now, at its core, we use the parallel advantage actor-critic algorithm. It is basically an actor-critic algorithm where we have several agents in several different instances of the environment collecting the experience at the same time. The experience is collected and used to update the network parameters in a single gradient update step. And in our case, we used 16 agents, and the training took approximately 1 day on a single GPU. In the plot on the right, you can see how the average episode length, which is the number of steps it took the agent to find a goal, changed during training. Therefore, lower values are better. We compare our algorithm with 3 baselines: the parallel advantage actor-critic and the proximal policy optimization, and also the Unreal. The parallel advantage actor-critic and the proximal policy optimization both failed to converge. The Unreal and our method were both able to find the target with almost 100% accuracy. However, while the average episode length of our approach was 42, it was 46 for Unreal, so our agent was more efficient. Now let me talk about how we achieved the transfer of our trained agent from the simulated environment to the real world. Basically, we use the following pipeline. First, we train an agent in a simulator, then we automatically collect images from our real-world environment, and then we fine-tune the trained agent on the collected images. Finally, the agent could be deployed to the real-world environment. In the third step, where we fine-tune the agent on collected images, we use curriculum learning to gradually increase the distance between the initial position and the target to help the algorithm learn. In the first picture on the right, you can see the Turtlebot robot that we've used for the experiment. After training, after we've applied the trained agent to the environment, the robot was able to reach 0.3 meter neighborhood of the goal in more than 86.7% of the cases. In conclusion, we presented a visual navigation approach that used deep reinforcement learning, and the goal was given by an image. Our method enables the transfer of the trained agent to the real world. The training algorithm was based on the parallel advantage actor critic algorithm. We used a different reward scheme and proposed some auxiliary tasks to help with the training. We've also designed a 3D environment simulator which is capable of domain randomization. And finally, we have evaluated our approach in the real-world environment, where the robot achieved satisfactory results. In future work, we would like to work with larger environments and also with continuous motion of the robot. We would like to use continuous actions instead of discrete ones. And we would also like to perform our experiments using a motion capture system for better accuracy. We would like to improve the domain randomization, which we hope will allow a direct transfer of the trained policy to the real-world environment. Thank you for your attention.